Hello everyone! In this video we will continue to examine topic 7.1, discrete energy and radioactivity, and in particular we will begin to unpack the idea of discrete energy and discrete energy levels in the context of spectra. But before we get into that, it's useful to discuss the original use of the word spectrum and where we've seen this before. And that is in the discussion of what is known as the electromagnetic spectrum. So recall that light is just one type of electromagnetic wave. This is a wave in electric and magnetic fields, as shown here, wherein we know that a changing electric field produces a changing magnetic field at right angles to it, and vice versa. And what this means is that if you change the electric field over here by, for example, wiggling an electron up and down in what is usually known as an antenna, that changing electric field will produce a changing magnetic field, and that changing magnetic field would produce a changing electric field, and so you get what is known as electromagnetic wave that propagates forward in space and can travel in a vacuum. They all travel at speed c equals 3 times 10 to the 8th meters per second, which is one of the postulates of the theory of relativity, which we will discuss a little bit of later in the unit. We know that they can be polarized because they are transverse and not longitudinal waves, and we know that the speed of the electromagnetic wave is equal to the wavelength times the frequency. In what is known to the IB as the wave equation, C equals lambda F. Now, there's one more incredibly important relationship that we will discuss the origin of in higher level a little bit later on in topic 12, and that's the relationship between energy and an electromagnetic wave. In most waves, the energy is proportional to the amplitude of the wave squared, just like the power. We showed that in topic 4 and in topic 9 more quantitatively. But light and other electromagnetic waves behave differently from that. In one of the sort of first hints that things going on at this scale might be different from things that go on at a classical macroscopic scale. In what is known as the photoelectric effect, initially outlined by Albert Einstein, it was discovered that the energy of a particular photon or packet of light, which we'll discuss a little later on, is equal to h times f. That is, the energy of light and other electromagnetic waves is proportional to its frequency, not to its amplitude squared. The constant of proportionality, as proposed by Max Planck, is known as Planck's constant. H equals 6.63 times 10 to the negative 34 joule seconds. So this is joule seconds. I'm sorry for the handwriting. And that means the energy of any particular photon of light, so that's a single light wave, for now anyway, is equal to a constant times its frequency. With higher frequency comes higher energy. With lower frequency comes lower energy. So very low frequency electromagnetic waves have low energy, and vice versa. This is unpacked and discussed and incredibly foundational for sort of quantum theory in general, as we will see. But what we need to know at this point, at the core level and for SL, is that this discovery was sort of foundational and from what is known as the photoelectric effect. And we will unpack the photoelectric effect in topic 12 at higher level. So, returning now to our discussion of the electromagnetic spectrum, if E equals hf, that is, if the energy of any particular wave of light is proportional to the frequency, then we can sort the electromagnetic waves that are possible into what is known as a spectrum. And that's where we split up the electromagnetic waves by their frequency or their wavelength. Notice, because they all travel at the speed of light, if you know the frequency, then you can immediately calculate the wavelength. And with this additional relationship, E equals HF, we can also go from frequency or wavelength to energy. So we can break down all possible electromagnetic waves by wavelength or frequency, or for that matter, energy. Optical waves, waves that we can see, are right in the middle, so to speak, although the middle is a little bit tricky. And higher frequency waves include the ultraviolet, on the violet side of the visible, X-rays, and gamma rays, where gamma rays are the highest frequency, lowest wavelength, and highest energy waves. Radio waves, on the other hand, are the lowest frequency, highest wavelength, and lowest energy waves. I would strongly encourage you to get comfortable with calculating energy, frequency, and wavelength when given those values using these relationships here. So E equals HF plus C equals lambda F gives us that E equals HF is equal to HC divided by lambda. That is a relationship that we will use a lot going forward. And the other big picture thing to recognize is that this idea of the electromagnetic spectrum is simply a way of laying out all the possible electromagnetic waves, all the way from radio at that low frequency, high wavelength, low energy side of things to gamma rays at high frequency, high energy, and low wavelength. Notice that this is an absolutely unbelievably large scale. Okay, so to unpack this a little bit, radio waves include waves that are kilometers long and a meter long. So that's a factor of 1,000. If you go a factor of 1,000,000 smaller, okay, you're barely at the lower edge of the infrared. Another sort of set of powers 10, so another factor of 1,000 brings you to the visible. Another factor of 1,000 and you're at the high end of the ultraviolet, low end of the X-rays. Another factor of 1,000, you're at the high end of the X-rays, low end of the gamma rays. And another factor of 1,000 and you're in the gamma rays. So this is an absolutely unbelievable scale. And this picture right here, this little diagram, is a little bit misleading because the wavelengths over here are literally kilometers long, and the wavelengths over here are 10,000 times smaller than a nanometer. So this is an extraordinary large scale and an extraordinarily large spectrum.